Hey everybody, my name is Brian Metzger. I am an application engineer here at Trimex Solutions, and my main focus, where I spend most of my time, is in the Solidworks simulation products. I am a simulation engineer, and today we're going to be talking about Solidworks flow simulation. This is going to be used to address any kind of fluid flow or heat transfer problems in your designs. Today's goals are going to be to give a basic introduction of flow simulation in SolidWorks. We also want to give an overview of the tool set and what you can and cannot do. We're going to look at three specific examples. We're going to look at an example of simple internal flow through a manifold. We're going to look at external flow in a wind tunnel. And then we're going to do a slightly more advanced example with some heat transfer for the purpose of optimizing cooling in an electronics enclosure. Now, when we talk about a traditional design process, when we don't have simulation, we're going to start out with a conceptual design, maybe a napkin sketch, maybe you sit down with your coworkers around a whiteboard and hash out what the basics of your design should be. Then you've got to do the details, and for most of us these days that means SolidWorks, right? We're going to use this advanced parametric modeling tool to work out where things are going to be fastened together, how much material we're going to use, thicknesses of walls, all sorts of different details can be worked out in SolidWorks to figure out what the design should be specifically for manufacturing. Now, if we're doing something that could possibly fail in the field, then we probably want to check to see if it's going to have a problem before we ship it out to our customer. So the traditional way would be to fabricate a prototype. We've got to make something that we can test and then do a bench test, see if we have any problems, if things overheat, or if we get the flow rates that are desired, whatever it may be. And if we do not pass that test, if we don't perform the way that we want to, then we've got to go back, sharpen our pencils, redesign, make some changes, and do the whole thing over again. Each time going back out to the machine shop, getting quotes, figuring out, waiting for time, waiting for, spending extra money on an additional prototype. And we go round and around and around this process as many iterations as necessary before we're happy with our results and we can manufacture something that we can monetize. And how do we validate these designs, either before or after the testing? Well, a lot of places that we talk to, it's basic engineering, intuition, and experience, right? We're very smart. We've been doing this a long time. We know our industry. We know what works, right? And that is good for a lot of people. You can base what you're doing on a previous design, right? We did something like this last year. Let's make it look like that. We knew that it worked. Maybe there's a better way, but we don't really know. We're going to play it safe. We're going to go with what we know. You can use recommendations for vendors for things like sizing a motor or a pump, or how much of something that you need to make a process work. This is good. Your vendors know their stuff, but my old professor used to tell me if you look for a recipe, if you call up the pepper company to get a recipe, they're probably going to give you a recipe with a lot of pepper in it, right? So we want to be cautious about this too. What we see more than anything, the most common answer we get is over-design, right? When in doubt, build it stout. Make everything way more than it needs to be. It's not the most cost-effective method, but it saves us all that iteration. We get something that works. Maybe we could have made it a little bit cheaper, maybe not, we don't really know, but we've got something, right? Finally, we test, right? We're engineers, we check things, we validate in the field or in some kind of a bench test that we can set up. Repeat, 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 repeat until we get what we want. And we're still doing that when we use a computer simulation product like SolidWorks Flow Simulation. The difference being that instead of going to the shop, waiting for a quote, waiting for all the time and the man hours and all the materials used to get that prototype ready and run what could potentially be a very long test, when we can do the testing in a virtual environment in SolidWorks, then we can go through a larger number of prototypes in a shorter amount of time with much smaller investment and go through more of those iterations so that we end up with a better design in less time with less money spent. So what we're trying to do here is compress this entire design cycle. We want to do our technical simulation, our validation concurrently with the original design, so that instead of building maybe 5 or 10 prototypes, now maybe you can get away with 2, right? Or maybe it works the first time and you go straight to manufacturing. That's a big difference. For a lot of places, the cost of one of these simulation products is less than a single iteration of building up a prototype of their design to test. That's not uncommon. And of course, even if it's built into your schedule, even if it's built into your budget, you run a functional test. If it doesn't go well, that is painful. That is really a problem. For example, this helicopter, when we go ahead, we build it all up, probably cost hundreds of thousands, if not millions of dollars to make this prototype, and we test it out, and what happens? We didn't consider the fundamental frequencies in the structure before we put it all together. This does not look good. This is not a good look on our design engineers when this happens. Even if it was just a test, right? That's a bad day. So what is design simulation? Let's define this a little bit more tightly, right? We're trying to predict our product performance and behavior concurrent with the design at the same time. We're going to try and avoid costly over-design. We're going to try and fuel our innovation and give us the power, give us the flexibility, the freedom to try more things, to go a little bit farther out there. Let our imagination be the only real limitation that we place on our design. We've got a lot of different things that we can test in Solidworks. Today we're just focusing on fluid dynamics and heat transfer, but we have Solidworks simulation, our structural simulation package. We can do rigid body motion simulation in Solidworks. We can look at environmental impacts, and we can do multiphysics, all really powerful tools. Today we're going to start out with a really simple example, internal flow through a manifold, and I've got this model up in Solidworks. Now I've got this part already modeled up, and I've added a couple of simple bodies onto the part. I've added lids, these 4 kind of caps on each opening. That's because I'm going to do an internal study. I'm going to do flow going through the inside cavity of the model. And in order to do that, I need the model to be watertight to define a computational domain. I'm sealing off the ends, and these lids are actually going to be used as boundary conditions. Flow is going to go in and out of my computational domain through these lids. And just to make things a little bit easier on myself, I always like to use transparency to my advantage. So I'm going to just quickly go into my visual properties and make this one body see-through. That makes things a little bit easier to do later on, right? So I need to create a flow simulation. I'm going to do this using a wizard. Now the wizard steps us through the process, and it lets us see what all our options are. The first page is just the project name, and I'll leave that at the default. Next, I need to set up my unit systems, and I'm mostly working in a metric system here. I'm going to make one little change here because I'm looking for head loss. Maybe I want to see how much is going through. So instead of measuring pressure in terms of pascals, I'm going to measure it in terms of inches of water. That might help me see pressures through this manifold. Maybe I want to widen up the pipes. I'm choosing an internal study, and I've got a couple options. I'll talk through these real quickly even though I'm not picking them. We'll look at heat conduction in solids later. We're always going to be measuring heat conduction in this system. That's always going to be tracked. But if we wanted to do maybe a heat exchanger or maybe an electronics enclosure or a boiler where some of the solid bodies are generating thermal energy, I might want to see the heat flow between those solid bodies and between the solids and the fluids. See how heat is carried away by the fluid. Not going to do that here. I can do radiation, more so in the HVAC package. We'll talk about that. I can do a time-dependent study if I want to see how long it takes for the flow to develop. Here we're going to leave that unchecked, and we're just going to do the steady state calculation, what the flow looks like after it's been running long enough to reach an equilibrium. I can turn on gravity if I want to see natural convection, where hot fluid rises, cold fluid falls because of changes in density. And finally, I can do rotation if I want to put in something like a fan blade that's going to spin and drive the flow. Next, I need to pick my default fluid. I'm just going to pick air out of the fluid database. And my wall conditions I'll also leave at the default. I'm going to use smooth adiabatic walls. I've got some initial conditions that I'm going to leave at the defaults as well. I'll use these later on my external study to define the flow direction. And finish. So I've got my computational domain going through the inside of my pipes. I need to define a few boundary conditions where the fluid is coming in and out of the computational domain. I'm going to do one here where flow is coming into the computational domain. I'm going to do an inlet mass flow, and I'll go with the default, a fairly small flow rate of about 1,000th, or I guess a 10,000th of a kilogram per second. That's still a good amount for this example, so we'll stick with that. And then I need to allow some flexible boundary conditions for flow to come out. Now sometimes it makes it easier when I'm doing this to do a section view, because on an internal study I'm always picking on the inside faces of the model. This way I can just pick them like this. So I'm going to do 3 pressure boundary conditions where the flow is going to come out. And what's powerful here is I'm not defining how much flow comes out. I'm going to find out by running this simulation how much air is going to come out the first, second, and third opening in this manifold based on this flow rate. Very, very cool. Now, I've actually done enough at this point to run the study. There's a couple more things I'm just going to touch on, but if I wanted to hit run right now, everything would go just fine. I can edit my mesh. Let's take a look at that. Now, kind of like in SolidWorks simulation, I've got a basic slider bar for this mesh. What the mesh is going to do is going to break down my computational domain into small, manageable chunks. Here we're using a cube mesh, right? Little boxes spaced throughout the computational domain, and we're doing a finite volume method here. We're tracking the fluid that comes in and out of those little volumes. If I push my slider bar to the right, I'm going to get a larger number of smaller chunks, right? That's going to give me more accurate results, but it's also going to take longer to calculate because there's more of them for the computer to do. So I'm going to leave that alone for right now, just where it is. We'll do a basic rough solution for the sake of demonstration here. Another thing I might want to do for accuracy is establish some goals. Goals are what I want to measure, what I care about, right? So what I'm going to do for my goals is I'm going to define a goal on each outlet where I want to check on the mass flow rate coming through each of those surfaces. I'm going to create a goal for each one so that I can see what percentage of the flow comes out of each of those, right? And that's really cool. That's going to let me see how the flow is divided up as it comes out. Maybe I want to make a larger or a smaller opening on one of them to coax more air out to balance this manifold, right? So that's really powerful. The goals are also going to define what the program is going to look for when it's deciding how many iterations it needs to run before it's finished. If I set a goal for one thing, it might take longer to converge on that than, say, another. Maybe flow rate's going to take a lot longer to converge than temperature. So depending on what I pick for my goals, it might take a different amount of time to calculate. That's all good for right now. I'm going to go ahead and run this project. It's going to run fairly fast because I've got a rough mesh and a fairly small computational domain. Now, the solver comes up as a separate piece of programming, a separate executable from SolidWorks. And we do it this way so that if you wanted to, you could actually jump back over to SolidWorks and keep doing other work. I get to kind of watch some of this happen in real time, which is a lot of fun. Watch the flow develop and watch as my goals start to converge. Now this one takes about a minute depending Actually, it only took about 17 seconds this time. Really quick, depending on what you're doing, depending on how complex and how fine a mesh, it could be anywhere from seconds to hours. It all depends. So once that's finished, I can view my results back in a higher resolution in Solidworks. First thing I might do is do a cut plot. A cut plot is going to show me my results by taking a two-dimensional slice through the three-dimensional volume of the computational domain. Let's kind of make this go through the middle here. And we'll maybe look at the contours in color of the velocity, and we'll take a look at the vectors with arrows. There's a lot of different options we can do on these kind of plots, and we can put multiple of them on the screen at the same time. Really, really cool, and what's especially nice about this is it's what we call a 2.5D plot. We're looking at a 2D slice, but if we want to, we can dynamically slide up and down throughout the computational domain, looking for hotspots, looking for areas of concern, right? Very, very cool, really great looking. These look great on a report, by the way, just because they are so colorful and interesting to look at. Just for fun, let's create a second one. Let's take a look at the streamlines. Going through. Oops. Very, very cool. Now that's a great 2D plot. That's a good kind of simplification, but we are working in 3D. Let's see if we can do a 3D plot to see everything that's going through. We'll do that with flow trajectories. We can see these streamlines as they go out of the inlet and out to the three different outlets of my computational domain. These can be animated. They look really awesome. Again, export this as an AVI for your PowerPoints, for presentations, and use it to get some design intuition, right? Take a look at another version of this with arrows. Really great, and I can't really emphasize enough, there are a ton of different options of things we might want to do to communicate what's going on to our coworkers. But at the end of the day, we're engineers, we need some numbers, right? We need to see what's going on throughout this flow. So let's take a look at a couple of things we can do for that. Well, one we might do would be a goal plot. Let's take a look at those three flow rate goals that we created, and we can see what the values are and how they balance out, right? And again, we might want to go back to the drawing board in our design and make some changes to the geometry to try to balance this manifold out. We're still in Solidworks, so if I go back and make a change to the geometry, all of my flow simulation is still all set up. All I've got to do is hit rerun and find out how my change improved things. I can even do parametric studies where I get the computer to blow through a whole bunch of different dimensions and tell me which one is the best. This is all really cool, and let me do one more thing here. I hadn't thought of this in advance, but we'll see how it goes. Let's make a 3D sketch here, and I'm going to make a line that I'm going to use for a plot. So I'm just creating a single line of a sketch that goes through the middle of the pipe. I'm going to use that for a plot in my flow simulation. Let's do an XY plot on that line. And let's say we want to measure the pressure and the velocity as it charges along. And there we go. We get these great XY plots throughout the volume. And it was just that easy to create, right? Very, very cool. So again, quick to do, easy, and all I've got to do if I want to make a change is pop back over into the model change my dimensions, add a body, subtract a body, change a configuration, and then I can rerun the simulation again and find out what works better. All at my desk without spending any extra money, without going out and using up other people's man hours, without adding time to my schedule. Very, very cool. So having done that, let's take a look at another example of what we can do. We just did internal flow. Let's take a look at what we can do for external flow. This is the exact same type of study, but just a slightly different twist on it. We're taking a body and we're having the flow go around the outside surfaces to see how they affect it. So back over into SolidWorks, I'm going to pull up this kind of isolated wing design. Now this is kind of a funky wing that I was able to pull down from GrabCAD. I want to see how it performs when I put it into a wind tunnel. I want to check for both the lift and drag that it's going to produce on the aircraft, and I also want to look at the torque that the flow applies to the wing to see if the attachment point that I'm going to design is going to be strong enough, if it's going to rip the wing off of the aircraft, right? So again, I'm going to start this off in the flow simulation wizard. This is what I use every single time. I'm going to keep most of the defaults here, both for the name and the unit system. That's all good. But I am going to say that I want to do an external flow study. The rest of the physical features I'll leave off. Again, for my gas, I'm going to pick air. I'm going to stick with my adiabatic smooth walls, but here in the initial conditions is where I define my flow rate. I want the flow rate to be in the x direction. You know what? I missed a step here. I wanted to define this in terms of miles per hour instead of meters per second. No problem. I just skip back to my units, change the base unit of velocity, and then jump forward again. No problem. 100 miles an hour, and finish. Now we get a computational domain that wraps a box around the wing. Now you can edit this computational domain, maybe make it a little bit smaller if you don't think that the flow effects are going to go out too far in the up or down Y direction. That's okay. We want to make sure that we're capturing enough volume around the wing so that we're not cutting off any turbulence, any eddies that come off of it, any kind of outside effects. We want to stay back from the action. I don't really need to define any more boundary conditions this time. I'm good to go there. I'm going to leave my mesh where it's at. All I need to do is define a couple of goals. Goals here are what I care about. And what I care about in this example are the forces that the flow is imparting on the wing, right? So that I can figure out what it's, what kind of lift and drag I'm going to get on the plane, think about fuel efficiency, think about what kind of maneuvers I can perform, and I'm also going to look at the torque that it's applying onto the plane to see if the attachment point is going to be strong enough. So I'm going to look for the force in the x direction, that's my drag, the force in the y direction is my lift, and I'm going to look for torque around both the z and the y axis. That's all good. I'm ready to run. This one might take up to a minute or so. Let's see if we can throw up a plot. And even go get a cup of coffee while it's running. Alright, so I've finished calculating. I can take a look at some results. Let's create a cut plot coming out maybe a little bit from the front plane. Take a look at the velocity, take a look at some vectors, and I want to bump up the density just a bit so I get a little bit more action in this plot. get a sense of what's happening. And again, this 2.5D plot can be traced along so that I can see what's going on. Maybe there's something that could be changed in this design, especially in this funky kind of wingtip that's been designed. Very, very cool. And I might want to do a 3D plot for the sake of better communicating to my colleagues what's happening. Let's get a lot going here. All right, there's my flow through the wind tunnel. Now this was easy to do, very, very easy. So changing the geometry, thickening up the wing, changing the angle of attack by putting it into assembly, putting an angle mate on it that I can vary. Simple as can be. I can do hundreds and hundreds of different studies in less than the time it would take to make a single prototype. So once again, you still need to test things at the end of the day, right? I'm not going to go and fly a plane on a wing that has only been tested here, but I might be able to get, 3 or 4 prototypes where before it took me, 6, 7, or 10. We want to bring that cost down, and we want to get a sense of what's going on. We do that again with our goal plots. So now we can see what all of those forces on the wing are. Very, very cool. And this gives us great insight into our design. So again, for external flow, very quick and easy to get a sense of what's going on around the wing. And this could be anything, right? This could be a car, it could be a truck. We could evaluate different changes to geometry to try to cut down on drag. It might be something as simple as a billboard. We want to see what the forces are from the wind. Finally, let's take a look at a little bit of a more advanced example, but really we're not doing anything terribly novel here. We're going to look at electronics cooling. We've got more bodies in our assembly, and we're going to add a little bit more physics by letting them generate heat, but we're doing the exact same thing that we did in the manifold. We just have an enclosure, an internal study, and we're going to look at flow in versus flow out. Now this one I've already set up, so I'm just going to talk through some of what I've done. When I was going through the wizard, I turned on the option for heat conduction in solids. That's going to allow us to have some of these solid bodies, some of the circuitry in this box generate heat. So I have to give materials to each of these bodies. If I take a look at the definition of these materials, what's really important is that they each have a density, a specific heat, a thermal conductivity, and optional a melting temperature. And that can either be a number that you punch in, or you can have temperature dependent material properties. You can do all sorts of different definitions, but the important thing is that it needs those basic material properties in order to calculate heat transfer. I'm also going to take some of those and define them as heat sources. Let's take a look at the chip that's underneath this heat fin. This one is simply defined as generating 5 watts of thermal energy throughout its volume. Now that heat is going to be drawn up into the metal fins of the heatsink, the aluminum heatsink, and it's also going to be transferred to the air that's flowing across the surfaces to draw that heat away. I've got an environmental pressure boundary condition on the 3 slots on the outside. That's how air is going to exit the enclosure, and I could have defined it, the inlet, the same way that I did before by just saying a particular mass flow rate if I knew it, but I don't really know what the mass flow rate is going in because I'm just going to put in a little electronic fan that's going to push air in. Now a fan can be defined as its own inlet flow, but instead of just defining the flow rate, a fan boundary condition is going to work on a fan curve. It's going to use a relationship between volume flow rate and pressure to figure out, based on the resistance that it feels as I run the study, how much airflow I'm going to get through here. And I might define that flow rate through that surface as a goal if I want to know what it is. I've got a series of goals defined here, things that I want to track, particularly the temperatures in the various important components. And I'm pretty much ready to run at this point. That's all I've got to do. Maybe 5 minutes of setup and ready to go. Let's load up the results here. And let's take a look at some of our plots. Most importantly, I've got a cut plot that's going to show the temperatures and velocities as I go through. Actually, this is velocity. Let's take a look at the fluid temperature as we go through the enclosure. And you can see where heat is being picked up. The cold air comes in and starts to pick up heat from the various components. I can also move this cut plot through the enclosure and look for areas where maybe I've got some stagnant flow that's not really helping me out. Maybe I need to up the flow rate. Maybe I need a bigger fan. Maybe I need bigger openings on the box. All sorts of different things that I could vary in my design, from the venting to the size of the fan, the number of fans, the placement of different components, and I can run through all different versions of this simulation, ultimately to try to optimize the maximum temperatures that are seen on these components, right? I want to keep the temperatures as low as I possibly can when they are all running at steady state. And the only way to know this is if I were to calculate all of the flow rates and flow patterns of the air going through the box. There is no way to do this on a pencil and paper. There's no way that even the smartest engineer is going to intuit how this is all going to go. You need to simulate it if you're going to do it without first building up a total prototype. And keep in mind, even in a functional test, you're not going to see the airflow like this, right? Any of these tests, to be able to measure something like pressure, you're inserting an instrument into your flow field and taking a measurement, which changes the results, right? So we get all of this great data that we can easily process and understand so that we can make conclusions and make changes to our design, make our designs better, get them to market faster, and spend less capital doing so that we can ultimately make more profit for our company. This is all big stuff. This is all really important. So taking a look at some of the options, we have our basic SolidWorks simulation flow package, and that's going to let you do a lot, right? We've got internal and external flow. We can simulate things like turbulence, heat transfer, non-Newtonian fluids. We can do compressible flow if you want to do Mach numbers up to Mach about 3 or 4. Can't quite get into the hypersonic range. We can do time-dependent studies if you want to see how long that circuitry takes to heat up, or if you want to do a non-constant heat load on something. And we can do rotating components. And one more thing to mention about that box, that could be any size, right? I did a little small electronics enclosure, but that could just as easily have been a factory with a giant headspace and a big boiler in the middle, right? Same thing. Now for specific examples, we might have some specific needs, so we have 2 optional add-in packages, modules that we can add on top of the basic flow simulation. The electronics cooling package is for people who are doing this to do serious study of electronics enclosure cooling. And what that's going to give you the ability to do is simulate some other more complex types of heat transfer, like 2 resistor components, heat pipes, PCB materials with the layers and different thicknesses. It lets you do joule heating and wires, and it gives you a big extended database of things like fans and heat sinks and different kinds of material properties. Likewise, if your main focus is kind of creature comfort and large-scale airflow and HVAC work, we have the HVAC module. That's going to give you the tracer study, the comfort parameters, and most importantly, the advanced radiation module. If you want to measure thermal radiation with a very high degree of accuracy, you need that HVAC module. It's also going to give you another extended database of building material properties and some other common definitions. This is all in the service of giving you better designs done in less time for less money. We here at Trimech are here to help you with that. Our mission is to help you create better, stronger companies and more profitable at the same time. So please give us a call, reach out to your local Trimech representatives, and we will match you up with the experts that can get you set up with whatever product that you need to get better designs out to your customers. I've been Brian Metzger. Thank you very much. This was a lot of fun. I hope you enjoyed it, and we'll see you next time. Thank you.